Yes, I'm not Jorge Vago. Vago is the project scientist of the EXOMARS mission, which is a mission by ESA, the European Space Agency, which is to be launched for the next part, as you will see, in 4 years. And because he couldn't be there, and I am involved myself there, and actually this presentation is a good follow-up of what we discussed yesterday, with the possibility for Mars and the Earth to have been co-evoluted early on. I more than accepted to present his slides. So most of these will be his slides. I have added a few at the end to make my own touch on this subject. So EXOMARS. So most of the question, if you have, you can ask me, but he would answer, of course, by email. So EXOMARS is, again, a mission which started long ago within ESA. It belongs not to the science program, but to the optional program. It's a mission which was not only devoted to make science, but also technology demonstration, to demonstrate that ESA knows 3 things: how to land on Mars, how to rove on Mars, and how to drill on Mars. And for historical reasons, this mission has been divided into 2 parts. One to essentially put the orbiter relay in space, and also because at one point the getting down the rover would have been done by NASA, and because ESA wanted to demonstrate also its own capability to land, a demonstrator of the lander, of the landing strategy, has been added to the launch of the orbiter. And that was part of the 2016 mission that was launched in March this year, and you arrived like months ago already there, and it's made of 2 parts. So the technology objectives is really to demonstrate the capability of landing. So the lander itself, as you will see, is rather small subject vehicle, which was supposed to make some science, but not a lot of science. It would have stayed on the surface for only a week or so. But essentially, ESA wanted to test its own capability of landing. But there has been some science objective added to the, not only to the lander strategy, but also to the orbiter. And the orbiter, which has a prime goal of making the relay for the future missions, not only the ESA mission, but all missions. And actually the system on board is a NASA system to capture all the data acquired on the ground on Mars for the future. It has also its own capability of making science with 4 instruments. And the instruments are essentially there to observe the atmosphere and to detect the rare gases. That's why it's called TGO, for trace gas element. So that's how it looked like before arriving. As you see, these are the 4 instruments I will go back to, and this is the lander, which is still attached at that point here. So again, that's essentially now a venture which is made in cooperation no longer between ESA and NASA, but between ESA and the Russian, Roscosmos, who replace essentially all the subsystems that NASA should have provided. And not only the launchers, the Protons, which has been used for TGO and that will be used in 2020, but also some of the instrumentation. On TGO, 2 out of 4 instruments have been made by Russia, and in 2020, as you will see, Russia is also an important partner. So these are the 4 instruments which are presently on board the orbiter. They have been commissioned November 22, actually, 2 weeks ago, and they are functioning nominally. This NOMAD instrument is essentially an infrared instrument capable of going, well, actually from the UV up to the 4.3 wavelengths in infrared, and with capability to point the sun also to make occultation, to essentially derive by occultation the composition of the minor species in the atmosphere. Similar to this one, ACS is the equivalent, but made by Russia at IKI, by Oleg Koroblov at IKI, which essentially covered the same wavelengths range and have the same objectives. We have a camera on board, Cassis, you will see design for that, which is supposed to make rather high resolution coverage of the surface, not as that high-rise do presently on MRO, but still. And FRIEND is also an instrument which is not a reflight, but similar to the non-neutron and spectrometer that the Russians have built, in particular on the ground for MSL. So, did I miss one? Yes. The orbit will be circular for TGO, but presently the orbit is highly eccentric. It has been a 4 days and now it's a 1 day orbit, so it's a very high apocenter, but it will be slowly made a circular orbit by one entire year of aero capture. It's also something that ESA wants to gain, not aero capture, but we want to circularize the orbit by essentially braking, it's aero braking in the atmosphere. So that will start in 2 weeks from now and for the entire year. And so next year will be devoted to some science, but essentially to circularize the orbit, and the real science will start in a year from now. One of the questions and one of the driver of this mission is, as you might know, the fact that methane has been discovered on Mars starting in the early 2005 by the PFS instruments on the Mars Express, the Vittorio Farmisano instruments, which detected some methanes. As you know, it has also been detected from the ground. It's evolved a lot in time and space, and it's always very marginal in the detection. It looks now, with the MSL measurement on the ground, that methane is a reality. It's a matter of a few ppb, no more than that. At some point we thought it might be tens or hundreds of ppb. It's probably much smaller than that. But it looks like it varies a lot along the seasons. And actually, as you know, it's a real question mark what the origin of this methane is. First of all, to confirm that methane exists and the origin of the methane. What is very abnormal is the variation on time, because you need an effective source of methane to replenish the atmosphere rapidly, and it's not clear what the cause of that. Of course, methane on the Earth, as you know, is essentially provided by not human, but living organisms, cause essentially, and so the question is whether or not on Mars also methane is a translator of the fact that there is some biology there, or whether it's a pure geological compounds, which also is a possibility. And the only possibility to try to discriminate between the different origin of methanes is to try to couple the methanes, if ever we can detect it, to other species that could be released at the same times, and the other species together with methanes can tell you what the real source is. So that's essentially the goal of this activity. The Cassis instrument, which is made essentially in Switzerland by Nick Thomas in Bern, it's a very specific, but I'm not going to enter the details here, way of making stereo imaging by rotating the instrument. So you make a cross here, you rotate it, and you try to make the same ground track in 2 different directions, as it's explained here. And with that, you should be able to make some stereo imaging resolution, which the goal is a 5 meter acquired for the stereo images. For the moment, what we have as stereo imaging, except for a few that HiRISE could provide on MRO, is the coverage by HRSC on Mars Express, which is limited to 10 to 15 meter in resolution. One of the goals, of course, of the neutron spectrometer is to know whether or not you have some epithermal neutrons, which would translate the fact that some of these neutrons have reacted with hydrogen, and if there is hydrogen, very likely it's in form of OH, not to say H2O. So very, very often the neutron detectors are called water detectors, and that's what we should be able to do on TGO with these instruments, which again is a Russian instrument. Schiaparelli is the name which has been given to the lander. As you know, the lander Venture went a month ago now. It was the end of October, 2 months ago almost. and it was not an entire success because it's been released correctly. All the subsystems looked to have worked properly in the sense that the parachute deployed, the shield was effective, but for reasons which have not well been understood yet, long oscillation of the system caused the gyro and the sensors to saturate it, and finally the computer conclude that we had reached the surface, although we were at 2 kilometers in altitude, and it's been completed by a free fall of 2 kilometers, and so it's crashed on the surface. So it's all by a success. The measurements made during the entry and descent were actively monitored, and that's a good thing, even science-wise. The first time we enter Mars during not a storm but a high dust activity, but all the payload that was ready to operate on the ground could not operate, of course. Part of that operated during the free fall. And one of the most important missing experiments is that for the first time we had the capability to measure the electric fields at the surface of Mars as a potential driver of this spider that, you know, we have a lot of dust uplifting, and the question was what the potential of Mars at that point. And that could have been very important also as a meteorological contributor. So that's the first part of the mission. The second part of the mission is due for 2020 now. It is really the core of the mission, because the core of the mission is really to land a rover there with a lot of payload that I will go to now. The idea now is that that will be driven by the Russians, in the sense that they will make both the launch and the system to the descent system. Sorry, excuse me. It's very, the schedule is very tight. For a long time, the minister themselves had to decide whether or not we would be ready and put the money on place to make this launch in 2020. And at the ministerial conference at ESA, you know, every 3 years we have a conference when the ministers finally decided what to do next. ESA being just an executive, they put the money in place for the 2020 to be the reality. So now the target goal, which is fully financed in principle. So 2020 will be both a technology demonstration, again, that the core that to land and to rove on the surface and then to drill, as you will see. But of course, if we do that, it's for science. So there are scientific objectives, and I will go to that. But essentially, the objective is trying to see if we have any biosignature in the sample that we analyze that we tell us that Mars in the ancient past, or Mars even now, has some living activity. And we will also, of course, measure the environment with a lot of different sensors. So that will be done in 2 places, one on the lander itself, because we will land first prior for the rover to be extracted and finally roved. So the lander himself will be equipped with instruments. At the first place, it was not envisioned. Now it is, because essentially the Russians want to equip the lander with a lot of measurement. There will be more than 10 instruments on the lander itself, and then the rover should go. So what we want, again, is to have access for the first time to material that will not be destroyed at the very surface by the environment itself. The environment being both UV radiation, the oxidant, and the deeper oxidant by the cosmic rays, down to the galactic cosmic rays. And the evaluation of the penetration of these is typically a little more than 1 meter, and that's why we will be equipped with a drill that will go down to 2 meters, potentially, not necessarily, but potentially up to 2 meters, to try to get as pristine possible samples. Pristine meaning not destroyed by any of the parameters that I put here. And these samples, after being extracted, will be analyzed in the rover. And we would like to do that over a few kilometers in excursion during the duration of the mission. So here you have a sketch of the drill when it comes here, and that the tip at the bottom, I'm not going to But the idea is not to make cores, I mean, not 2-meter cores, but to make very small cores, a few centimeters in depth, at depths down to 2 meters if we need that, and to bring them back to the rover. So the nominal mission will be something like 6 months, 218 souls. We would like to have at least 6 stations in which we will make the entire cycle of experiments. Each excursion will take typically 2-3 weeks, 16 to 20 souls to get there, to choose the samples. We have, as you will see, possibility to select the right samples, the right site, and the right samples afterwards. And the rover typically is a 300 kilogram mass. It's typical, similar to the MERS rovers, but the payload is entirely different. And we have typically a few kilometers autonomy here in driving. But again, the goal is only a few, typically 6 months. That's typical of what on the mast, there is a mast, you might have seen that here. You have a mast here with some instruments here. The instruments are twofold, cameras and infrared spectrometer. And what you see here is essentially the top part of the mast with both, we have a NAC, a WAC, the narrow angle camera, 2 wide angle camera, and at the center we have a point infrared spectrometer. The point spectrometer, which is named ISM, is made by the Russians at EKI, and all the rest here is made in Europe, both by England and Germany. It's a highly cooperative venture, and you will have the capability to make that sort of scope here in almost real time if we need, both for locomotion and for science. Again, I go rather fast. If you have any question, of course, please just ask. When we are somewhere here, just close to the drill, there is a camera which is called CLUPI. This camera will be a closed camera capable to image really the samples, not the sample when they are drilled, but the environment down to resolution, which is sub-millimeter resolution. Locally, we should have even 40 micrometer. So this idea, with that, we should be able, because the drill and all the things afterwards will take a lot of time, so we want to be sure that when we start to make the experiments on samples of interest. So the close-up imager that you see here have different possibilities. It's at the end of the drill here, so it can work when the drill is deployed or before the drill is deployed, essentially to analyze the different places here to know where the drill should go and when the analysis should take place. So you have the sort of things here, and typically you have the sort of resolution when you are very close by, you are close to 40 micrometer per pixels, but typically it will be more than 100 micrometer per pixel. So that will be the sort of scale at which you will be able to select the right place to drill afterwards and to get the samples. The subsurface drill, I will not enter in deep condition. It's to get to 2 meters, it's a set of 4 sets of 50 centimeters, I don't know the name in English actually, subsystem I would say. So you drill first 50 centimeters. When you have finished, you take the other part here and you put it on top and you go another 50 centimeters. And so finally the tip goes to 1 meter and so on up to 2 meters if you need that. It takes some time, and we will not do that many times because each evening we have to store back all the system to avoid it to be stored at very low temperature at night. So it will be long, and very likely we will first work with a 50 centimeters possibility, and then at the end, or if there is any need to do so, we'll be able to go down to 2 meters to measure in the same places the variation of properties as a function of the depths, in particular to see whether or not there has been some modification of the surface material by the oxidant or the cosmic rays. That's the way the samples will be delivered. I think I have a better view here. So the drill will deliver the samples in here. There is all this is what we call the laboratory itself, the ALD. And you will see it's a very complex structure here. That's never been done before in space. Neither the MERS, the rover, the MSL, even Mars 2020 doesn't have all the capabilities that we have here. We are not very good in system, but we are rather good in instruments. And so the samples will be put here, and then the samples will be injected in this structure here. And as you will see, maybe better here, there is a complex suite of treatment of processing of the samples prior to be analyzed. And this is very, very complex, and the qualification of that is not completed yet. That's why we won't be ready prior to 2020. That's why the 18 launch has been postponed to 2020, essentially because we are not ready demonstrating all that. So the samples will come here, and then all this suite here that I will not really enter, we have the possibility to crush the samples to make powder if we want. We can also bypass them if we also want to. So we can crush there. We have some dosing station to know exactly how much samples will be delivered to different instruments here, and we can flatten the surface, also the samples when they are in the container here. And the containers finally are in this carousel here, in which you have 32 small ovens and one what we call refillable container, a flat surface that we can clean also and exchange afterwards. And the reason is that all these different ovens here, the samples will get there, and you have the possibility by stepwise heating to measure the composition from the volatile to refractory things. You can go to very high temperature if you need, and as you will see in a second, you can also make derivation here. So that just to show you that it's a very packed and complex thing here, but the basic idea, I am not going to detail all that. These are the different dosing station. This is very small. This is 3 millimeters inside, so it's really very small. So when the samples are brought here, the idea in the LD is to make 3 instruments sequentially from the less destructive to the more destructive. And we have the capability to measure the composition of the samples down to the grain scale or the microscopic scale. We want to have the composition down to 20 micrometer, and that will be done by an infrared microscope that has never flown in space at that level yet. So that's what we call the micro-omega instruments. Then it goes to Raman spectroscopy, and then to MoMA, which is the Nether and German instrument that will make laser desorption, mass spectroscopy, plus gas chromatography. It's a very complex structure here. So because time is running, I will go rapidly now to these essentially ways things will be finally processed, but that's not the most important here at that point. So again, you have here the list of the instruments that will be packed here. Typically the track here will be a few kilometers, 6 stations as I tell you, and typically 2 to 3 weeks to get from one to the next. So where shall we go? These are the places in which, because of the altitude, we are limited to go. So that's where we will be. Finally, we'll go in the ancient terrain here. And for those who are aware of that, the 3 places that we have selected now are essentially these 3. Competition during the 3 is still open. Mars Valleys, Oxyaplanum are those which are considered the best preserved sites, giving access to what happened prior to the LHB, prior to the 4.2 billion years activities. We know that we have identified all these essentially with what I told you yesterday. They are rich in phyllosilicates, and more than that, you have even stratification over there. So principle, from one strata to the next, you can really follow the environment change over the time. And if in one of the samples you have some carbon-rich material, you will know that possibly some activity happened at that point. So these are the 3 sites in competition for the moment. So that's the summary of what I just told you. And just to finish, I will go back to what I said yesterday to show you how ExoMars enter in 2 minutes, if I have 3 minutes, right, to tell you how it opened. I told you yesterday that the beauty of Mars is that very early on, it has probably that sort of things. Life might have started in some of these places, but what is the beauty is that some of these sites, and at least 2 out of the 3 which are pre-selected here, are exactly the sites which we considered have preserved the record of what happened 4.2, 4.3 billion years ago. And doing that, we have access to the early Earth probably, because we consider that probably the same process happened on the Earth. So if habitability means looking for a site which had stable water, liquid water at the surface, these are probably the unique site in the solar system that can tell you that actually similar process that happened on the Earth and elsewhere being there. So we are very happy with that, if we go there. One of the questions, of course, which has not been asked now, water to me is not sufficient. What I said yesterday about the contingency, you need to have the right ingredients, and I will go back to that in a second, that immerse in the right water. Right water meaning the right temperature, the right pH, the right acidic component, the right borate, as said yesterday, for example. A lot of things that will make this activity very rapid. To me, to start from these ingredients to the first cell, the membranes, whatever, has to be very fast. If not, water will just destroy everything. It's a matter of days, probably. So you need to have the right water. Water is not sufficient there. So what else? And you have two other things, phosphorus things and carbon. For the phosphorus, I think there is no problem because we had continents and the leaching of the continents replenished with phosphorus. So to put phosphorus in the oceans is not a problem. The real problem is carbon-rich species. And as I said yesterday, to me, the important thing is that most of the organics are in these comet that we have looked at, and I will just finish by that. You know that phyla is here. And the reason why I show that is to show that where we put phyla finally, if I can say so, it came at rest in the best place we could think of. Why? Because after all jumping here, in this place, which is when you increase the resolution, it's right here. So you see that it's really in a fantastic place because it's an alcove prevented here it is. It's really in a place which is totally preserved from all the outgassing. And we could demonstrate that during perihelion, while all the surface was moved by 1 meter or so, our system did not move by 1 millimeter. So it's really a highly preserved, pristine material is there. So all the material that we analyze, that you see here, is really the outer solar system material. That's a very dark material, carbon-rich, and this is really the take-home message that this material that was present in the early solar system is not made primarily of ice, but of organics. And as some of you know, I have proposed that this material be named not organics, but organize. You put an E here, and it's really tell that the ice is embedded in the organics. What I said that is that the fact that we rebounced show that the upper structure of the comet is a crust, solidified crust, and that's very important because when such a body enters the planetary atmosphere, it was shielded, protected, and all this material here could be embedded in the oceans here. So that's sort of fundamental. So this is the material that went in the early times to the oceans on the Earth. This is really what we hear. And what I wanted to finish with is that, to me, we have here all the ingredients which finally could be used as the molecules or the compounds out of which you can really start to build the real life. It's not living molecules. To me, life is not the synthesis of molecules. It's the process by which all the ingredients immersed contingently in the right environment at a given time can build the living structures. The big frustration we have with phyla essentially is that there is a single instrument measurement that we wanted to make that we couldn't make because of lack of time. We just need another hour, no more than that, to demonstrate in particular that one of the key property is already present there, and I will finish by that, when I said that we have all the enabling properties. The chirality, which is, to me, absolutely fundamental. We need to have some excesses out of which, by autocatalytic selection reaction, how you will just increase to go to homochirality. These excesses very likely are already present there, as we saw them in many meteorites. The reason being that, at the end of the evolution of the disk, most of this material, which is already in form of carbon-rich grains of rather large size, as you saw in the images, is 2-3 millimeters in size, they could have been irradiated by the early sun, which by its own polarization could have really polarized the system, informing some excess of chirality. That has been demonstrated in the lab by Louis Landecourt in particular recently, and that to me is really fundamental. And I will stop here. Thank you.